So our next speaker for today is Anubrotaa Bhuniya. She is a BSc third year Maths honors student in Vishwabharati University. She attended MTTS 2021 in level O, and she would be speaking on torsion of a curve. Yeah, Anubrotaa, are you here?
We're talking about curvature and torsion of a space curve. So, well, when we say the word curve, we think of something which is in some way is actually one-dimensional. So, the simplest way to define a curve in R3 is by defining it by parameters. So, let me recall the definition. A parameterized curve in space is a continuous function alpha I to R3, where I is an interval in R. So here the parameter is the variable we are taking in I, the interval in R. So now if we think physically, a curve is something we can get from a straight line, right? If we think physically that from a wire, if we want to make a circle, then we just have to bend the wire in a certain way to get the circle. But if we want to get a helix, then like we studied about solenoid, right? So when we are making solenoid, we just have to twist the wire around a something cylindrical. Okay, so we have to twist the here I am saying the word twist in a proper way. So I want to physically mathematically explain how we can twist or bend a wire. Okay, so here in mathematics, if I have given a straight line, how we can get a curve from a straight line? So I am taking some conventions. I'm taking the parameterized curve like this, such that alpha double dash c exists for all p belongs to I. Alpha dash c is not equal to 0 for all p belongs to I. And this alpha dash c cross alpha double dash c is not equal to 0 for all p belongs to I. Now, let me give some examples of a space curve. This is a circle. Okay, this is a plane curve actually. In the xy plane, the circle lies of radius a, and here the parameter t, you see alpha t. By parameterizing, we can define the circle by taking alpha from 0 to 2 pi to R3, defining it like alpha t equal to a cos t, a sin t, 0, where a must be greater than 0. So what is the parameter t is here actually representing? It is actually representing the angle, this angle. The angle of the radius vector is taking with the x-axis actually. I have messed up. Okay. So again, I was talking about a helix. So a helix is our space curve actually, a function 0 to 2 pi from to R3, defined by alpha t equal to a cos t, a sin t, bt. A greater than 0 and b can be any non-zero real number. So here a denotes actually this radius. When we are taking the projection of any point on the xy plane, a is denoting the radius, the length of the line joining the origin and that projection point. And b is the how much the curve is rising above the plane in one rotation. And t, the parameter is here denoting this angle again. So see, we are actually getting a helix by rising but first cutting a circle, then rising it above the plane in a certain way. So if we want to express it mathematically, we have to actually define two quantities, right? One denoting the bending, the other denoting the twisting. That is what actually curvature and torsion are respectively. Curvature is nothing but how we bend a straight line to get a particular curve, and torsion is the quantity that expresses the twisting to get a space car. Now we have to first start with a straight line, right? So the straight line, how we get it? Here there is a definition of arc length. ST, we are taking some point from the interval as the initial point, and ST is the length of any point alpha t from that point alpha t0 for a curve alpha. So it is defined by integration t0 to t norm alpha dash tau d tau for all t belongs to I. See that this S function is strictly increasing and continuous on I, and thus it is invertible. So t can be expressed as a function of S, right? By taking the inverse of it. So say t equal to ts. Now alpha t equal to then becomes alpha of ts, and so alpha, this we can denote by alpha bar s. So see, if we start with a parameterized curve alpha parameterized by a parameter t, then we can reparameterize that curve or that function by s, which is actually our arc length. We call this parameter s as an arc length parameter. Okay. Let me demonstrate it with an example. Let me take the circle of radius a. So here the arc length becomes at any point t, integration 0 to t, I have taken 0 the initial point, norm alpha dash tau d tau. Then norm alpha dash tau is equal to a, so the integration becomes at, st equal to at. So we can write t as s by a. Thus our alpha bar s becomes alpha s by a, and that is nothing but this point. So we are getting another representation of the same curved circle. But what is the benefit? What is the benefit we are getting from this? Here the parameter t, as I have said, denotes this angle. Okay. Now to get this angle, we have to fix the origin as the point where we are taking the angle. So if we want to define a circle here, and we want to take O as the initial point, then it would be difficult. But here for S, we don't have to take any initial point outside the curve. We have taken alpha 0 as the initial point, and that is exactly same whenever we are taking the curve, wherever we are taking the curve. And alpha t point, that is the same point we are taking on the curve. Like if we take this point as alpha t and this is as alpha 0, then see, if we are taking this helix here, then again this point remains our initial point, and this point remains an arbitrary point, and this length remains the same. So the change of the parameter s doesn't depend on the position of the curve. This helps a lot later on. Now the helix I have talked about is given by this. Okay. Now to go further, I need to introduce some more notions like tangent vector. Here you see alpha bar dash a is nothing but alpha dash t by ds dt, and here ds dt is equal to norm alpha dash t. So alpha bar dash s is becoming a unit vector, which is alpha dash t by norm alpha dash t. We're defining this vector alpha dash s as ts, the tangent vector, the unit tangent vector at any point. You can see here, this is alpha dash s, and this is what dtds or alpha double dash s is. Since ts is a unit vector, alpha double dash s is always perpendicular to t. Okay, now we are defining the normal vector. Okay, I've said already that dtds or alpha double dash s is perpendicular to t. So we are taking the unit vector along dtds as the normal vector. We call this now. See, if we take a curve in space, there can be many normals. Actually, there can be a normal plane which is normal to the tangent vector. So when we fix a normal vector. Here we are giving the name of this particular normal vector, which is given by dTds by norm dTds as principal unit normal. And this normal vector always points towards the concave side of a curve. That is this side, not this side, okay? Why this is happening? Because dTds always points toward actually the concave side of the curve. Since we are taking ns along dTds, it is actually pointing towards the concave side of the curve. Now, there is a plane, you see, there is a unique plane at any point to any point consisting of the vectors c and n. We call this plane as osculating plane. The actually osculating plane serves as the tangent. You see in a plane curve in R2, what the word tangent does in R3 in space, the osculating plane does the same work. It actually instantaneously contains the curve. The vector perpendicular to oscillating plane is called the binormal vector, and C and B together forms a right-handed moving frame. C and B. Okay. So this moving frame we can use later on it to define canonical form of a curve. Now I'm getting C and B for the circle. We are taking the reparameterization of the circle by the Euclidean parameter, and C here becomes like this, N like this, and see B, here B is a constant vector. Whatever the point alpha s is, at that point B is becoming a constant vector. And see, this is actually nothing but it is pointing towards the positive z axis. And that is what we want, right? We want to denote the plane that contains the curve instantaneously as the osculating plane, and now we are taking the normal on the plane. Here, since this curve alpha s, the circle, remains wholly on a plane, that is, it is a plane curve, its normal must be constant. Since at any point the plane, the oscillating plane here becoming the xy plane. Again, we are getting B, C and B for the helix. Now, we want to define the bending of a straight line to get a curve, a space curve. Now, to bend, we have to think it like in the oscillating plane. Okay, so what do I take bending as? Bending is something we do on a plane. So here I have taken the projection of a space curve alpha s on the oscillating plane at a point s0 and denoted it by beta s. Now we can prove a very interesting theorem that gives us that if we take alpha, if we take any space curve, any plane curve in R2, then in that plane, if we shift to the initial tangent point, that if we shift the x-axis to the tangent, initial tangent, then norm dTds is equal to d psi ds, where psi is the angle that the tangent to alpha at s makes with x-axis. We have done this. Since t is always a unit vector, norm dTds denotes the change of the angle. Okay, the change of the angle that the tangent is making with the x-axis. Now, if we take the projection on the oscillating plane of alpha s and denoted by beta s, then beta s becomes a plane curve. And so, for this plane curve, norm dTds denotes the change of the angle, and this change of the angle, how the tangent is moving along the curve, is nothing but how the curve is moving. So we can take norm dTds as a quantity that denotes how the curve is bending, right? Actually, this is defined as the curvature. kappa s equal to non-BTDS equal to non-alpha double dash s. Now see, since kappa s is equal to norm of some vector, kappa s is always greater than 0.
Yeah, Anubrotaa, you have only
Yes.
5 minutes left.
Okay. So for kappa s for a plane curve, that is circle, is given by 1 by a. And for this helix, it is actually a by root over a square by b plus b square. So if we want to get a certain curve just using this bending, we can't get it. Because see, if we take a circle of radius root over a square plus b square by a, then kappa s becomes a by root over a square plus b square. And so we are getting two space curves with the same bending. So just taking bending as a quantity, we can't get a particular curve. But we have a theorem that we get a unique plane curve if we take just unique plane curve. If we take the rigid motion in our, if we take the rigid motion, then it just changes the position, but we are getting a unique curve in the plane. Okay, so now we want to mathematically express the torsion of a curve. What is torsion? We are moving the curve upward from the plane. We are moving it from the plane. So we can take it as a change of the binormal vector, right? Since binormal vectors is normal, it is denoting the change of the curve from the plane. Or we can take it as the change of the oscillating plane. How the oscillating plane is making new angles with the oscillating plane through the taken point. But here comes a problem. If we take non-BBDS, similarly as before, as we have taken non-BTDS as the torsion or as the twisting, what comes the problem? For helix, for the previous helix, we are getting non-BBDS as mod b by root over a square plus b square. But here, see, if we take beta b greater than 0, then this is the curve we are getting. And if we take beta less than 0, this is the curve we are getting. We can't get, now these two curves, they are not same. We can't, anyhow, we can't make, through any rigid motion, we can't make these two curves same. But we are getting the torsion same. So if we just want to take just the kappa and the torsion, then we will getting two different curves in the space. But we don't want that. We want to specify a particular curve with using just two quantities. So where we have to assign a sign to non-BBDS. Now see, BBDS is parallel to the normal vector. This is how we get it. Since BBDS is parallel to normal vector, BBDS dot n gives us non-BBDS with assigned a sign, which is actually cos of the angle between the normal and BBDS. Now here is the result that if we take T as the x-axis, n as the y-axis, and b as the z-axis at any point, then alpha s rises above the plane towards the positive z-axis if BBDS lies, the direction of BBDS is opposite of the y-axis, that is ns0, and it rises down and it goes down the oscillating plane or the xy plane here if BBDS points towards the positive y-axis. So basically, what we're getting is BBDS dot n is equal to minus non-BBDS, which is less than 0, if ZS is greater than 0. And BBDS dot n is non-BBDS, which is greater than 0, if ZS, I'm denoting this as ZS, if ZS is less than 0. Now what do we want? We want to define a quantity that takes positive sign if the curve alpha s goes upward when that quantity is positive. But here it is happening opposite thing. When this is going upward, dvds dot n is negative, and when this is going downward, dvds dot n is positive. So we just can take minus dvds dot n. We're defining the torsion of a curve alpha at S as minus dvds dot n. See, for the planes of the torsion is actually 0. Since ds is equal to a constant vector and dvds is equal to 0, 0, 0, and so tau is becoming 0. So for a plane curve, we don't need twisting. We just need bending. That is kappa, which is 1 by a for this surface. And here for the helix, when we are taking norm dvds as the twisting quantity, it is giving us a falsified statement that it is equating two curves, okay, which are actually different. But here, if we take minus dvds dot n as the twisting quantity, then tau is equal to b by root over a square plus b square, and it is taking the sign of b together with it. And so these two curves, they are actually then different in our notion, since we are getting two different twisting quantities for these two curves. Okay, so finally there's a theorem, fundamental theorem of local theory of curves, which is actually saying this physical thing mathematically, that if we know how to bend a straight line and twist a straight line in a particular way, then we can get a unique curve. Okay. And what is the straight line here? Here, straight line is the total length of the curve, which is actually the interval in which the arc length parameter s is moving. So here the statement of the theorem is, given continuous functions kappa is greater than 0 and tau is, where s belongs to I, there exists a regular parameter called alpha I to R3 such that s is the arc length, kappa is the curvature, and tau is the torsion. Moreover, any other curve alpha bar satisfying the same conditions differs from alpha only by a rigid motion. So we are getting a curve regardless of the position of the curve in the space. If we just are given two continuous functions, one is positive function, kappa is greater than 0, the other is tau. So what we want to get mathematically, the physical thing, that from a straight line we are getting a curve just by bending and twisting in the proper way is given by this theorem, where the bending is denoted by kappa and tau denotes the twisting. I'm done.
Okay.
Okay.
Yeah.
So
thank you, Anubrotaa.
For references, I want to say that Vector Calculus by Susan Jane Coley is a very good read, and Manfredo P. Carmo, Differential Geometry of Curves and Surfaces, Andrew Presley, Elementary Differential Geometry, and by Thomas and Frenet, Calculus and Analytic Geometry. These two books by Carmo and Presley, they are a bit of advanced read, but this book by Susan Jane Coley is very easy to read. And Thomas Frenet, it is actually a high school level book, but it has really good theory about these things. And for further read, I want to suggest you guys the Elementary Topics in Differential Geometry by John A. Thorpe. It mainly covers the surface very, very properly, and in the last portion, it has curve covered. And the expository article by Professor A. Kumarishan, Frenet-Serret formula. It is a bit advanced. So I am suggesting it for further read after reading these books.
Yeah, okay. Thank you, Anubrotaa, for the nice talk.